one of the highlights of this program is the fact that we got another Volt because we wanted to tear it down. A lot of you look like you perhaps were here in 2007 when we tore down the Toyota Prius. So we wanted to do the same thing with a Volt because when we started this program with Avnet, the idea was to celebrate innovation and then to tear apart, what at the time was the most innovative EV on the market. And it's got knocked around a little bit publicity-wise. But having spent the last 9 months in that car, I can tell you I dreaded the fact that I was going to be driving around in a GM car. I'll be honest with you, it's the most comfortable car I've ever driven in my life. It's amazing. And as you're going to see today and over the next 3 days, the next 2 days, the design engineering, the automotive electronics in this thing are amazing.
So just kind of looking at the battery pack itself, you can see it's located underneath the vehicle of the car. It's held with a number of fasteners around the perimeter of it. It's actually a big stamped sheet metal piece, and it has a number of cross members across it that bolt in place, or they're actually spot welded in there. And then it's got this big cover over it. It's a compression molded cover that covers up the whole battery pack itself. It's a sealed unit. As we take the top off this battery pack, you can see the components that are underneath it. So we pulled the doghouse, there's a big silver thing sitting on the case over there. I'll refer to that as a doghouse. So once we got that off, we could find the components that make up the battery pack. As you can see, there's a number of different cells in here. It's actually got 4 different cell packs inside of it. There's one in the front, there's one in the middle, and then the big T-shape at the rear of the battery pack is actually split into 2 different cells. On top of each of those is a control module. The control module is a direct interface to the cells themselves. And those will be looking at the temperatures and the voltages across each cell as we look at them. The left rear corner of the battery pack is an 18-cell module. Each of those cells have a voltage probe on them, so they're monitoring every cell within the battery pack. In addition to that, they're also monitoring the temperature of the battery pack, because the temperature is very critical in the life expectancy of this battery. You got to have it at a controlled temperature. If it's run too cold, if it's too hot, it's going to degrade over time. And I don't think GM wants to pay the warranty prices prior to the 10-year warranty that they claim on it. But we kind of approximate where those current or those voltage sensors are within the battery pack. They're spread out about between every 4 cells. There's actually 288 cells total in the battery pack. Up in the top, you can see what they do is they take 3 cells and connect them in parallel. Then those parallel cells are all connected in series. So think of this battery pack as a Christmas tree. If one of those go bad, they all go bad. You're going to have an open circuit. So it's basically you're going to have 3 cell packs connected in series. So in the 18 cell pack we talked about just a minute ago, you can see there's actually 72 cells within that. All right, so now this is kind of an overview of the entire battery pack itself. When you look at it, you can see the very front of the pack actually has 30 cells. The middle pack has 24 cells. The right rear also has 24 cells, and then the left rear has 18 cells in it. So what they've done is they actually run a coolant through in between the cells themselves. In the bottom, you can kind of see like where the green is. We're not sure exactly how many cells are touching, but they do claim that they touch every cell in the battery with coolant. So if you could just envision those 3 cells in series or in parallel, they're probably running coolant between the 2 of them. And then the next pack, they're doing the same and so on is how they're running the coolant through there. But it comes into one side, runs around to the back, and then it goes through the cells, and then it exits out the other side of the battery pack itself. You can see on the front of the doghouse, there's a red and a blue circle on the very bottom of the doghouse. That's actually the coolant lines that are connected to it. Those coolant lines are stainless steel, and then they route up to the radiator module up in the front of the vehicle. There's also a heater for cold weather. When it's in a cold weather environment, you have to heat up the battery, so they actually have a heater for the coolant. So they pump warm coolant into the battery pack to bring it up to temperature. Then they'll start cycling it to cool it and so on. The one thing I'd like to note on it is there is no sealed connectors on these modules. These are all open, so I know there's questions about what happened with the one that Nishta tested. Well, when you start thinking about it, there's no sealed connectors. You can kind of figure out the circumstances that they put themselves in.
Before I get into the electronics and the control system for the battery pack, I thought I'd like to frame it by talking a bit about how much energy this can hold, because of course the goal of the car is to reduce gas consumption and allow you to drive around in a purely electric mode as much as possible. This battery pack weighs 435 pounds. It is about 5.5 feet long. So it's a very big object, and it will move the car about 35 miles. 35 miles is roughly the distance you can go on a gallon of gasoline, which weighs about 6 pounds. So if you, on a weight basis, gasoline is 72 times more efficient than this battery pack, which is using state-of-the-art lithium-ion chemistry. So I think the message there is that the wall for entry, a truly competitive electric vehicle, is very difficult. Gas is a very dense energy source. And as we get into the battery pack and some of the control systems, you'll see what it takes even to get it to this level. What you can see here is a control system that is used to monitor and modify the lithium-ion cells that are in the battery pack. On the left-hand side of the slide is the monitoring electronics, the boards that sit on top of the lithium-ion battery pack. We'll talk a little bit about that. Electronically, that's where most of the interesting stuff is going on. The stack of batteries is indicated by this blue series combination here of battery symbols. And as Al said, there's 96 of these cells in series along here. Each cell consists of 3 prismatic lithium-ion battery cells, measuring 5 inches by 7 inches. What the electronics does on the left-hand side is it monitors current, voltage, and temperature at every point along this series stack. You have 360 volts DC that's falling across this series stack of battery cells. And so these guys are rated at 5 volts, or in the case of this circuit, this integrated circuit, it's approximately 70 volts. Obviously, you have to be careful about your ground and power planes, and what they use is a series of virtual grounds. We'll be seeing that in a minute. And virtual powers, power supplies that are established at various stages along the chain of the battery cells. On the right-hand side, you've got the main microprocessor unit that sits at the front that Al will show in a couple of minutes. Its job, amongst others, is temperature control, relay control, current sensing, running the diagnostics, sending the output to the main vehicle electronics. One of the things I find interesting about this system is that to get the extended life of the battery cells, you have to control the temperature very precisely of the vehicle while it's sitting there. And so the goal by GM is to keep that whole battery pack with a variation of no more than 2 degrees centigrade across the whole system and in time. And so what you have is a coolant loop that can also function as a heater in cold weather, and a pump that circulates that, and these temperature sensors strung along the battery cells, changing the temperature. And what I find interesting about this is that it's not just during the operation of the vehicle that this thing is monitoring and operating, but also during the charging process. So when you drive it home and it sits in your garage and you plug it in overnight, this thing will be cooling or heating as required. Over here is the communications line, okay, the communications interface, and everything's nicely isolated electrically by optocouplers along here. Again, because you have this huge voltage range falling across the cell stack. And in this particular case, you have 4 identical, or very close to identical pieces of electronics that are collecting that information, okay? And they break it up into virtual ground islands, as I was discussing on the schematic, to make sure that the electronics can accommodate that shifting voltage level along the stack. Each one of these 4, if you look at the lower left, has a ASIC on it, or ASSP. That is made by LG Chem, and I'm going to talk about that for a few minutes. And then controlling that is a Freescale microprocessor with 32K of flash on board. So relatively simple processor collecting the information and sending that out to the vehicle. One thing I like about this is that they've conveniently color-coded these boards. So this board is at the high end of the voltage. It's orange. The intermediate one is blue. And then the 2 ones near the ground strap are both green. We're now looking at a decapped version with the package removing of that LG Chem silicon, okay? Looking down there, This is manufactured in a collaborative environment between STMicroelectronics and LG Chem. ST actually makes the silicon, and what it does is it senses voltage and current, and the sense inputs are along the bottom and the left-hand side of the die. We've got in the center of the die standard cell logic that does all of the digital processing that's necessary, and then you have larger control circuits that we haven't really looked at yet. Each one of these LG Chem dies can take 10 inputs. That's 10 voltage or current controls from the series stack of lithium-ion cells. BCD stands for bipolar, CMOS, DMOS. So that's a combination of three basic silicon fabrication technologies that you have available. It's proprietary to STMicroelectronics. This particular one. The bipolar is used when you're trying to measure very slight voltage levels. We'll see in a minute why that's necessary. CMOS is used for the digital processing, and then DMOS is used for high voltage levels, because in automotive you have to handle both very precise voltages and very large voltages to drive the control signals. So one of the reasons that you need precise voltage sensing is because the voltage levels on these individual lithium-ion cells have to be measured to within millivolts in order to extend the life of the battery pack as a whole. If one of the cells starts going out of whack, you have to take corrective action to compensate for that in a process called cell balancing. All right. This is a block diagram of the L9763. It's that specialized chip that I've been talking about. One of the things it does is operates the cell pack over only 65% of its total range charge. Okay, so if you have your electronic toothbrush, you recharge it and you discharge it, you can do that 300 to 500 times before you really start to compromise the lithium-ion cell. Over a 10-year lifespan, you might have to charge and discharge this thing 3,000 times if you do it once a day. That's it. So to extend the lifespan of the cells, what they do is they operate at over 65% of the range. And if it goes below a minimum threshold, the gasoline engine turns on and it starts providing electric charge so you don't fully deplete the battery pack. The other thing they do is each individual cell, because it's monitored, if it gets overcharged, it does something called passive cell balancing. What it will do is it will take a resistor that's in parallel with an individual cell and then short it out. So if the cell gets overcharged, you do the cell balancing process, you pass current, divert it through the resistor instead of through the battery, so you can't overcharge your batteries. My final comment is that we always talk with the engineers back home, and when we're taking this apart, is like, what are they trying to do with this thing? What is it designed for? And if you look at it, you come up here afterwards, you take a look, you'll see that for example, the coolant loops are connected using hose clamps, things that you can put your cottage pump together with. And the whole thing has the look and feel of something that's in evolution. It's not really designed yet for millions and millions of vehicles. It's almost like a prototype. So our feeling is that this design is going to evolve substantially. The chemistry is probably going to change as they learn more about how to make these things. We'll see changes in the mechanical design and in the cooling of the pack. And they've gone into this design process with that in mind, so that they'll be able to change things very rapidly over the next few years.
Well, and the thing I'd like to add to that too is just the modularity. When you look at those battery packs, they're all identical, and it's just basically how many do you add in length and how do they grow. John was kind of fortunate, I think, with these modules, because I actually did a project for the EPA just determining what the cost of these new technologies would be. And we did an LG Chem battery pack prior to this. It was actually out of a Korean-built vehicle. And they really do a really good job of laying that battery or that circuit board out. You can kind of see how what it's doing. If you were to look at a Ford Fusion, you look at their board, it doesn't make any sense. But this one, it just jumps at you. It says, I'm doing this. This is for monitoring. Here's my controls and so on. It's a really simple and really easy, simple way to make it a modular. So you can see now you had 4 different groups. You just keep growing them for every module you need to add to the battery pack.